Hello, my name is Alberto Pascal, and today I will be sharing with you my approach on the traffic problem from the CS50 artificial intelligence course. First of all, I would like to start running my code because it will take a while for it to actually get the results. So let's leave it running and come back later. And then let's go to the explanation. Some background, the objective is to try to teach the AI how to recognize traffic signs by analyzing images. And let's get started. The load data function gives us ppm images that we need to analyze using the CV2 module. And how will we load them? We will scan the directory, and for each image found, we will use the read image from CV2, resize the image with CV2 resize, append the image to a list of images, and then keep track of the root directory from the image in a list of directories. So we can finally return a tuple of image list and label list pairs. And the get model function, to solve this, we need to create a neural network using TensorFlow's Keras module. We need to test out different convolutional pooling hidden layers, and we need to compile the neural network, finally returning the compiled model. In the image here, you can see my final result, in which I have two convolutional layers, two max pooling layers, the flattening hidden layer, and the final output layer. So how did my testing go? To start with my testing process, I first began with a neural network that was based on the classes example, which included a convolutional layer with 32 filters, max pooling, flattening, hidden layer with 128 neurons, 50% dropout rate, and the output layer with a soft max activation. And this had a very poor results. This had a 62% accuracy with a 1.19 in loss. So I started trying to improve by playing around with the sizes of the convolutional layers and the pooling layers and increasing the neurons in the hidden layers. I saw this was counterintuitive because my accuracy dropped down a lot when changing the size of the pixels, probably due because my images were pretty small. So I went back to the original sizes and increased the number of filters from the convolutional layer, saw a small increase. I played around adding a second convolutional layer and pooling layer, and I saw a bigger increase. Then I tried playing around with filters from both convolutional layers, but increasing the dropout. And then again, our accuracy decreased a lot because we were not making full use of our potential in the neural network. So I went back to the original dropout rate and added a second hidden layer, which was no huge improvement nor a decrease in accuracy. I tried reducing the number of neurons in the hidden layers to play around, and the impact was pretty small. So I decided to remove the second hidden layer and increase the neurons in the first hidden layer. Then I tried adding a third convolutional layer because it was what was working the best up to now, but it was decremental, having our accuracy drop to only 5%. So I ended up removing the convolutional layer, playing around with the dropout, and ended up discovering that I could change the activation functions from the convolution networks. I changed them both to SALU and saw there was an increase in accuracy in the process, but the end result was practically the same. So I merged them and had a ReLU activation function for the first convolutional network and a SALU activation function for the second, which netted me my best results yet. The best results I could get was a final accuracy of 96% with a .15 loss. So let's go and see how our program ended up being. Here we can see we had a loss of .07 with an accuracy of 98%. That would be it. Thank you all for watching and see you all next time.